In this video, we're going to start chapter 7, and 7 is on alkyl halides and then nucleophilic substitution reactions. Chapter 8 is also going to be on alkyl halides, but specifically elimination reactions. And then at the end of chapter 8, we're actually going to combine the material from both 7 and 8. So chapter 7, alkyl halides. And nucleophilic substitution reactions. So remember our 4 common types of organic reactions. We had substitution, elimination, which is what we're doing in chapter 8. And then we also had addition and rearrangement. So substitution is where we're breaking one sigma bond and we're forming another sigma bond. We're literally going to substitute. Nucleophilic means it's a nucleophile that we're going to be substituting with. So alkyl halides, remember that was a carbon bonded to a halogen, and I'll write that down in a minute, and then substitution reactions. Just kind of looking ahead, chapter 8, this is also going to be on alkyl halides. So Rx being my abbreviation, R being a carbon-based group, X being a halogen, and then we're going to do elimination. And then again, at the end of chapter 8, we're actually going to combine the chapter 7 and 8 material. So you'll have a section on alkyl halides and then differentiating between substitution and the elimination reactions. So alkyl halides, a little bit more about those. I said that it was a carbon bonded to a halogen, and then specifically it's going to be an sp3 hybridized carbon. So I have an sp3 hybridized carbon, so a carbon bonded to 4 things, and then one of those things is going to be a halogen. So an sp3 hybridized carbon bonded to a halogen. X being our abbreviation for a halogen, so fluorine, chlorine, bromine, or iodine. You can have halogens bonded to sp2 carbons, but they're not going to undergo the types of reactions that we're going to see in chapter 7 and 8. So while it is have a carbon-halogen bond, they're not going to undergo the substitution and elimination reactions that we're going to look at in these next couple chapters. We can classify our alkyl halide as being primary, secondary, or tertiary. Again, Rx is going to be my abbreviation for alkyl halides. We can write that up here. Again, R being a carbon-based group, in this case, sp3 hybridized carbon bonded directly to that halogen. So we can classify our alkyl halide as primary, secondary, or tertiary. So our first one, primary. And we can use a 1 with a degree sign, so that's how we would symbolize primary. And a primary alkyl halide is going to have the carbon that's bonded to that halogen is only going to be bonded to one other carbon. So I'm going to bond that carbon to one other carbon, and then it's going to be bonded to 2 hydrogens. So R in this case is again a carbon-based group. Secondary, our symbol is 2 with a degree sign, but we're not going to say 2 degree, we're going to say secondary. And this one, the carbon that my halogen is bonded to 2 other carbons. Let's use an R group, sorry. And then 1 hydrogen, right? It has to have 4 things if it's going to be uncharged. And then tertiary, we can use a 3 with a degree sign, but again, if we were to read that out loud, we're going to say tertiary, not 3rd degree. And I bet you'll never guess, but the carbon that the halogen is bonded to is going to be bonded to 3 other carbon groups. We can actually define a methyl alkyl halide, and that's where the carbon is not bonded to any other hydrogen. So a methyl halide. So it's essentially, you would have a methyl group bonded to the halogen. So primary, I have to have one other carbon group attached to it. So this R group is a carbon group. So primary, the carbon that the halogen is bonded to. So this carbon, right? That's the carbon that my halogen is bonded to one other carbon. Secondary, this carbon that my halogen is bonded to two other carbon. In tertiary, this carbon that my halogen is bonded to three other carbon. In a methyl halide, my carbon that the halogen is bonded to is not bonded to any other carbon, right? It's just three hydrogen. So some examples, we want to classify these as primary, secondary, or tertiary. Alkyl halides. So I'm just going to draw a couple here. Okay. So the first one, what do you think? By first, I'm going left to right. Primary, secondary, or tertiary? So if you're saying secondary, you're correct. If you're not seeing it at all, let me show you. So my bromine is attached to this carbon right here, right where I put the purple dot. And then that carbon is attached directly to two carbons. So that carbon where the purple dot is attached to that carbon, and then it's attached to that carbon. This carbon here is attached to another carbon, but I don't really care about that. I only care that the carbon that the halogen is attached to two other carbons. So this is going to be secondary. How about the one in the middle? What do you guys think? This one's tertiary, right? This carbon is the carbon that my halogen is attached to, and it's attached to 1, 2, 3 other carbons, so tertiary. How about that last one? This one is primary, right? This is the carbon here that my halogen's attached to, and then that carbon is attached only to that carbon. Now that carbon's attached to two other carbons, but that's not what we're looking at, right? We're looking at the carbon that the halogen is directly attached to, and then we're seeing how many carbons that is attached to. So this carbon right here is attached only to that carbon, so primary. Other types of halides that you could see are allelic, so an allelic halide. These ones are going to have a multiple bond adjacent to the carbon that the halogen is attached to. So I have my halogen attached to this carbon, and then one carbon over, I have a multiple bond. So this would be considered allelic. I could have benzylic. There's actually just one L in benzylic. And benzylic halides have a benzene ring, which we haven't really talked about much, but it's a 6-sided ring, so 6 carbons in a ring, and then it has alternating single and double bonds. And then attached to that, I have a CH2 group, and then that is attached to my halogen. Now, be really careful with these two to not get them confused with what I'm about to draw. So a vinyl halide This is the one that's often confused with allelic. In a vinyl halide, that halogen is directly attached to the carbon that has the double bond. And then arelic, sometimes just aryl halides, these have that benzene ring again. So 6-sided ring with alternating single and double bonds. But then directly attached to that is my halogen. So be really careful with these. The big difference is that the vinyl halide, I forgot the L, and the arelic halide, the halogen is attached to an sp2 hybridized carbon. So remember I said that the halogen has to be attached to an sp3 hybridized carbon to undergo the reactions that we're going to see in 7 and 8. If you're given a vinyl one or an arelic one, they're not going to react. So just be really careful with these two, right? If I look, this is sp2, it has 3 electron groups. This is also sp2. Compare and contrast with allelic, this is sp3 and this is sp3. So these are technically not alkyl halides, right? These are not going to undergo the reactions in chapter 7 and 8. So if you're given one of these and you're asked to state what the product is, you're actually going to say no reaction because they're not going to undergo those. If you came across these in lab, no reaction, we're not going to expect them to react. So just be really careful. Remember, our alkyl halide needs to be an sp3 hybridized carbon attached to that halogen. With vinyl and arelic, you have sp2. Arelic sometimes, I think I said this but didn't write it down, sometimes we'll just say an aryl. It won't have the ick part on the end of it. So again, just watch out. sp3 hybridized carbon bonded to that halogen. The next section in the text is on nomenclature, and we have already covered the IUPAC nomenclature for alkyl halides, but I do want to talk a little bit about some common names. So nomenclature, not clatures. So our IUPAC rules, we've already talked about that. So just a real quick example. Remember, we're naming them as substituted alkanes. So if I put a bromine on this carbon, I have 4 carbons, so bute, it's an alkane, so it ends at ane. And then on my second carbon, I have a bromo group, so 2-bromo-butane. I'm not showing any stereochemistry in this one, so I wouldn't add R or S in front of it. If I was to add stereochemistry, this would be chiral, and then I would need to give that designation. So IUPAC, that we're hopefully good with. Common names, however, are still sometimes used, so I do want you to be familiar if you see these, kind of what they're talking about. So a common way to name them, so not following the IUPAC rules, is to name them as alkyl halides. So you would name the carbon-based part as an alkyl group, and then you would add the halide to the end of it. So if it's bromine, bromide. So named as alkyl halides. And this only works for simpler ones. If you have something that's, more complex, it's hard to name them this way. But in a lab setting, you may come across it. So if I was to draw this one, right, our IUPAC name, I have 3 carbons, 1, 2, 3, would be 1-bromopropane. If I was to name this as an alkyl halide, I would say, okay, I have 3 carbons, but I'm going to name it as an alkyl group. So instead of propane, I'm going to say propyl. And then I have bromine, I'm going to name it as a halide. That means I'm going to modify that ending. So propyl bromide would be the common name for this. Again, IUPAC, let's write that down. Right, the rules that we use, 1-bromopropane. We could This is similar to the one I did above. I just want to use another halogen. So IUPAC for this one, 2-chlorobutane. If I was to use the common name, right, if I want to name it as an alkyl halide, I actually would have a sec-butyl group, right? If I was to look at this part, right, and name that, my halogen is attached to that second carbon. So if I was to name that group as an alkyl group, I would have sec-butyl, and then chlorine would become chloride, so sec-butyl chloride. Again, it's not something I'm going to really ask you to do. I just do want you to be familiar with it. So, common names. Looking at some physical properties. So my alkyl halides are weakly polar, right? I do have a polar bond between carbon and that halogen. So weakly polar. Because of the carbon-halogen bond, right? My carbon is less electronegative than most of my halogens. So it is partial positive, my halogen partial negative, right? It's more electronegative, and those electrons are being pulled towards that halogen. So because it's a polar molecule, I do have dipole-dipole interactions. With alkanes, I only had London dispersion forces. So it does have dipole-dipole interactions. As well as London dispersion forces. Right, it does have electrons. Those electrons are moving. They can be arranged unsymmetrically, inducing dipoles in neighboring molecules, right? So I have dipole-dipole interactions as well as London dispersion forces. So if I was to compare the boiling point of an alkyl halide to an alkane with a similar number of carbons, the boiling point of that alkyl halide is going to be higher, right? I still don't have any hydrogen bonds, right? I don't have an oxygen, hydrogen, fluorine, hydrogen, or nitrogen, hydrogen bond with lone pairs on the oxygen, nitrogen, or fluorine, right? No hydrogen bonds, but I do have dipole-dipole interactions, right? Higher boiling points than alkanes with a similar number of carbons. Let's actually say the same number of carbons. So if I wanted to compare ethane, right, just 2 carbons, its boiling point is negative 89 degrees Celsius. And if I wanted to compare that to 1 bromoethane, this one is 39 degrees Celsius. So at room temperature, ethane is a gas. My bromoethane is a liquid. My boiling point and melting point both actually do vary as the size of the R group varies, and then also as the size of the halogen varies. So my melting point and boiling point both increase as the size of the R group, right, the carbon portion, increases. An example, we'll use my 1 bromoethane again. But then let's compare that to bromobutane, 1-bromobutane. So my boiling point, 39 degrees Celsius, this one, 102 degrees Celsius. So as my number of carbons got bigger, right, my boiling point went up. As I change my halogen, my boiling point and melting point are also going to change. So the boiling point and melting point increase as the size of the halogen increases. And remember, those increase as I go down a group in the periodic table, right? As we go down a group, my valence shell is getting larger, right? As my valence shell gets bigger, it extends into space further. So if I was to compare bromine to chlorine, bromine is going to be larger. So using our example here, 39 degrees Celsius. And then if I was to compare it to 1-chloroethane, so that's like a chlorine, this one is actually going to be 12 degrees Celsius, right? Chlorine is smaller than bromine. So as the size of my halogen got bigger, right, bromine's the bigger one, it has the larger boiling point. Looking at our chemical properties, this is also going to be determined by my carbon-halogen bond. So the chemistry of alkyl halides is determined by the carbon-halogen bond. Right? Again, it's a polar bond. My carbon is my partial positive, right? It's less electronegative than my halogen. So those electrons are being pulled towards that halogen. What that does for us is it makes this carbon electron poor, right? This carbon is electrophilic. So a nucleophile, right, can donate electrons to that carbon, right? It is my electron poor substance. So two characteristic reactions of alkyl halides. Our first one is nucleophilic substitution. So as I just said, a nucleophile can actually attack that electrophilic carbon. So first one, substitution. And that's going to be the primary focus of this chapter. So we're going to learn about alkyl halides, and then the rest of the chapter will really be on nucleophilic substitution reactions. So we're going to have our alkyl halide. I'm going to add some sort of nucleophile to it, and we're going to substitute the halogen for that nucleophile. So I'm going to have a carbon nucleophile bond, and then that halogen will be by itself. So remember, we're breaking a sigma bond, we're forming a new sigma bond with a substitution reaction. Specifically, right, we're breaking a carbon halogen sigma bond, we're forming a carbon nucleophile sigma bond. So it breaks the carbon halogen sigma bond, and then we form a carbon to that nucleophile sigma bond. Our second type is going to be elimination reactions, and that's going to be the focus of chapter 8. So elimination. And elimination reactions, remember, we're forming a pi bond in these ones. So I'm actually going to draw this one out a little bit differently. I actually want to show, because we have to put a carbon-carbon double bond in here. So I need to draw 2 of my carbons out. So I'm going to have my halogen here, and then some R groups attached to it, and then some R groups attached also, and then 1 hydrogen. I'm going to add a base to it. Our base is going to be our electron source. The way that we're going to differentiate between the base and the nucleophile is that this base is actually going to grab my proton. So instead of attacking that partial positive carbon, that's what my nucleophile is going to do. My base is actually going to take this proton. The electrons between that proton and the carbon are going to go down between those 2 carbons, and then I'm going to kick my halogen out because my carbon would have too many bonds, and then we'll end up with a pi bond between those 2 carbons. So I'm going to end up with a double bond between those carbons. I still have my R groups on here. And then essentially my conjugate acid, right? That base grabbed onto a proton, and then I do have my halogen floating around somewhere. So we're forming a new pi bond. Right? We're producing an alkene as my product.